we are all here. So this story starts with the discovery of Ceres by the Italian astronomer Giuseppe Piazzi, the 1st January of 1801. He was able to collect 21 observations in almost 1 month. Then the object was lost, and so we had the problem to recover the object. This is a problem of orbit determination, in the sense that from observations of a solar system body we want to compute its orbital elements. Well, then Carl Friedrich Gauss was able to solve this problem, and a year later we were able to recover Ceres. The method by Gauss consists in 2 steps. In the first step, a preliminary orbit is found. There is a polynomial of degree 8, so please take in mind for those of you that do not know this, that the degree is 8 for the method of Gauss. And then this preliminary orbit is the first guess of a least squares method. Okay, let me introduce some quantities that will appear throughout all the presentation. We are dealing with optical observation, so we need 2 angles, the right ascension alpha and the declination delta with respect to the celestial equator. So, other quantities are the heliocentric position of the asteroid. Here we assume, as in Gauss method, a topocentric position of the asteroid. So, ρ is the topocentric position of the asteroid, and we assume to know the position of the, say, observer here. And what we don't know is the radial position and also velocity of the object. So let me also introduce the definition of a 2-short arc of observation. So a short arc is called VSA if, in other words, with respect to those that are written there, the geodesic curvature is not statistically significant. And this can happen, for example, when we have 2 observations, or when the accuracy in the observation is poor. So essentially we have a certain number of observations given by alpha and delta that I introduced before, and all the information can be represented by the attributable, which is this vector here, and is made by alpha, delta, and their time derivatives. And the attributable is referred to the mean epoch of the observation. As I said before, we don't know the radial distance of the object and the radial velocity. So the topic of this talk is on a new method of linkage. With linkage we mean to join together 2 of these VSAs of observation in order to form a preliminary orbit that fit all the data. Well, then another problem is the identification problem. So with the modern telescopes and those that are going to be operative in the next future, like the large synoptic survey telescope, we will have a huge amount of data. And so from one side we have an improvement in technology. From the other side we want to be able to follow this improved technology. We want to be able to build with this data. And so consider 3 observing nights. If we use Gauss method, essentially the computational cost, the complexity of applying Gauss method, trying to identify triples of observations, is in the order of the cube of n, where n is the number of observations per night. This number 10 to 5 is referred to, for example, these next generation telescopes like the LSST. Another strategy could be instead to consider just the first 2 nights, use a linkage method, is expected a computational complexity in the order of the square of n, and then, well, we have identified some pairs in the order of n, could be some under some simplified assumptions. And then we consider the third night, and we try to identify triples of VSAs. And with this alternative approach, we have computational complexity in the order of the square of n. So the challenge is to find an efficient linkage algorithm, where here the word efficient is referred to Gauss method. So I remind you before that I said that the degree of the polynomial in Gauss method is 8. So efficiency is referred to that degree because our aim is to put the linkage problem into a polynomial form. So in this sense, the first attempt was made by Taff and all, using the conservation of the integrals of motion. So we are making very simplifying assumption that the motion is Keplerian, and so we have conservation of integrals of motion. But they were not able to find a polynomial formulation. They used the conservation of the angular momentum and the energy. The first successful result came by Gronchi, Di Mare, and Milani, and using the conservation of the angular momentum and the energy, they were able to find a univariate polynomial of degree 48. Univariate in the sense that it's a polynomial in one variable, and the variable is the radial distance, which is the unknown. Gronchi, Farnocchia, and Di Mare were able to improve this result by using, instead of the conservation of the energy, the conservation of the projection of the Laplace-Lenz vector along a suitable direction. And the degree, in this case, is 20. Here we show a better result in this sense. So polynomial whose degree is even lower. So here, in the next slide, I will go quite fast because, for example, here we have the integrals of the two-body problem, the angular momentum, the energy, Laplace-Lenz vector. We have also to take into account these well-known relations. What I'm going to show here is the dependency of this quantity. So C is the angular momentum, and then the next slide, energy and the Laplace-Lenz vector on the unknown. So we see, for example, here that the angular momentum is linear in the radial velocity, quadratic in the radial distance. The vectors D, E, F, and G are known. They depend on what we call data, that is the attributable at time t1 and t2, and the position velocity of the observer, Q dot. So here we have the energy. We put in red this critical term in the sense that for what we want to do, to put the problem into a polynomial form, this is critical because we have a denominator, and moreover, we have a square root of a quadratic polynomial. I consider here the Laplace-Lenz vector, again this term, and this is this expression just again to show the dependency of this expression, the unknowns, rho and dot. Well, this is the first result that I'm going to present. Given two attributables, and assuming that they refer to the same object, we consider this system which represent the conservation of all our integrals, the angular momentum, Laplace-Lenz vector, and energy. This is a system of 7 algebraic equations in the 4 unknowns. One referred to the first epoch, 2 to the second. We have 2 VSAs, so we are trying to linkage these 2 VSAs. And the goal is to search for a polynomial system that is consequence of 1, and which leads to a univariate polynomial of equation of low degree. Here we use low, this term. Well, then I will give a more exact explanation. We found an optimality property of the degree of this polynomial. So what we did is, well, this first step is the same one that was used in previous work. We project the conservation of the angular momentum along 3 independent directions that are related to these vectors. They are known, as you can see from their definition. Position of the observer and line of sight unit vectors. Line of sight unit vector is the unit vector of the radial, of the position vector of the asteroid with respect to the observer. Well, this is a quadratic polynomial Q in rho 1, rho 2, and these 2 equations are used to eliminate rho dot 1 and rho dot 2 because they are linear in these two unknowns. Then we have to consider the conservation of the other integrals of the motion. And if we define C in this way, we find that C does not contain anymore the term that I called before critical is 1. And this is good for what we want to put the problem into a polynomial form. Then the monomials with the highest degree are all multiplied by this vector. And we have a third remark that if Q is equal to 0, then C is parallel to C. And C is equal to C1, which is equal to C2 because we are assuming that we are using also these two equations here to delete the radial velocity. Well, so instead of this system, if we consider this system, Q equal to 0 and C equal to 0, it is reasonable to project the vector C along E rho 1 and E rho 2 because in this way we also eliminate the monomials of highest degree. This is what I'm showing here, but it's also at this point useful to consider this remark. If Q is equal to 0, we have also that this relation is automatically satisfied. So this also means that since delta Q is in general independent on these two vectors, we can consider this system of 3 equations instead of 4. In other terms, we take C, we project it along only 2 directions instead of 3. Well, I just want to remind that P1 and P2 contains the highest degree polynomials in P1 and P2 are of degree 5 at this point because of these smart state projections. So the result of this work is the following. Equations 8 can be reduced to a system of 2 univariate polynomials of degree 10 and the greatest common divisor has degree 9. Okay, this polynomial has at most 10 solutions, but now I will not go into the proof of this result. So since we are people that like fitting data, here we are doing a linear regression based on what? The polynomial degrees that we obtained so far, 48, 20, and 9. 48 in 2010, 20 was the result of the paper in 2011, and this last result in 2015. And we ask if we can do better. Well, maybe we can do even much better. This linear regression tells us that essentially the number of solutions is 0. Well, this is not a joke, because if we consider this system and we add these other two relations, so this is a polynomial system with these two other variables, Z1 and Z2, well, this system is generically inconsistent. And this is a system of 9 equations in 6 unknowns. The reason is that, okay, if we have a poor Keplerian motion and we have no errors in the observations, and the two attributables belong to the same object, okay, the solution exists, but in general this system is inconsistent. So now we'll conclude my presentation with the result that has been published this year by Giovanni Glocco, myself, and Andrea Milani. So if we delete these two relations, we drop them. We have the conservation of the integrals, but we have inside this expression Z1 and Z2, that is, these are polynomial expressions. Well, this system is consistent. This is the result. And we can prove that the univariate polynomial of degree 9 is the polynomial which has the minimum degree among all the univariate polynomials that are generated by this ideal. Okay? So this is a polynomial ideal in the polynomial ring given here in the variables ρ1, ρ2, and their derivatives z1, 2. So the elements of this polynomial ideal are obtained in this way. These are 7 polynomials. We multiply each member of this ideal by another generic polynomial that belongs to the same polynomial ring, and we sum these terms. This is a generic polynomial. Okay, this is the main theorem. So for generic data, we can find by hand a set of polynomials that is a Grabner basis of the ideal I for this lexicographic order, and such that the last member of this Grabner basis is the polynomial of degree 9 that we found in the previous paper. So a set of polynomials like this is a Grabner basis for the ideal I if the leading term of a generic polynomial of the ideal is divisible by the leading term of one of the members of the Grabner basis. This is a kind of definition that I can give you now for the Grabner basis. Lexicographic order, well, when it is applied to the alphabet, the lexicographic order is the one that we find for sorting entries in a dictionary. Okay. And we are using this ordering here. I don't have too much time for the proof, but we'll try to conclude giving the main idea. Well, these are the members of the initial ideal E. We are doing the same projections for the angular momentum difference that I showed you before, and we made other projections for the difference in the Laplace-Lenz vector. The idea is to exploit these two relations to eliminate the radial velocity, and then to work a little bit on the Riemann polynomials, these ones, especially maybe it's useful to show this set of polynomials. P4 now is linear in Z2, and P5 is linear in Z1, while these two polynomials depend only on ρ1 and ρ2 if we eliminate the radial velocity. We show that these polynomials, the hat just wants to indicate that we deleted the radial velocity, are, apart from this factor, P1 and P2 that I introduced before. So we can consider the elimination ideal, this one made by Q, P1, P2. The elimination ideal is the intersection between the initial ideal and the polynomial ring in the variables ρ1 and ρ2. And we introduce other two polynomials with a tilde here, by exploiting this relation that follows from q equal to 0. The nice property is that these polynomials are linear in ρ1. These are the Newton's polygons that are referred to q, p1, p2, p1 tilde, and p2 tilde. And the idea is to find ideals that are equivalent to each other. So first of all, we show that this ideal j tilde is equal to j. Then we introduce other two polynomials. And look, this is the univariate polynomial of degree 9 of the previous paper. We first showed that this ideal is equal to this one, and the little bit more difficult part was to show that then this ideal is equal to j tilde, which is equal to j. And at this point we end the proof. Our Grabner basis is made by q equal to 0, is made by q, q2, q3, then p6, p7, and then we have w and u. So this is the last slide. The polynomial u follows from the proof of the theorem, has the minimum degree among the univariate polynomials in the variables either ρ1 or ρ2 that are generated by the polynomial I. So now the next step will be to use this nice and I hope efficient linkage method to large databases of observation that are there, and for example the isolated tracked file of the Minor Planet Center, together with other methods. And so with this I conclude my presentation. So thank you.
We have time for a short question.
Short question is, I think that your approach is rather not very, but similar to the approach of Laplace. Because if you deal with rho and rho2, so you can can calculate the orbit, but on only circular orbit. If you add the second derivative, then you